Welcome back to this tutorial on upper motor neuronal control of movement. Now I'd like to turn our attention away from the cortex and into the brainstem. My learning objective for you here is that I want you to be able to discuss the neural centers that give rise to medial descending projections from upper motor neurons in the brainstem to lower motor neurons associated with the ventral horn of the spinal cord and even in the brainstem itself, in the motor nuclei of the cranial nerves. So our brainstem upper motor neurons include primarily two sorts of populations of cells. There's a population of neurons associated with the vestibular nuclei, and we've talked some about these in a previous tutorial. And then there is a population of neurons that emanates from the central core region of the brainstem. That is the core of the tegmentum of the brainstem. We call this core the reticular formation, and the reticular formation really extends throughout the entire brainstem, but the portion of it that gives rise to projections to lower motor neurons is primarily found in the pons and in the medulla. Okay, so let me just take a minute or two to remind you of the projections that arise from the vestibular nuclei and descend and terminate in the spinal cord. You'll recall that there are vestibulospinal connections that are concerned with mediating reflexes that are sensed by our vestibular apparatus, and the sensory signal is going to be some kind of an acceleration or movement of the head. So this movement could be a rotational acceleration of the head, which would be sensed by our semicircular canals. It could be a linear acceleration or a tilt of the head sensed by the otolithic organs. And these signals might very well necessitate an adjustment of posture. And in postural adjustments imply that there must be some change in the output of the spinal cord involving the axial muscles, the proximal limb muscles, and perhaps even the distal muscles of the limbs. And these reflexes connecting head movement to postural adjustment are mediated via these vestibulospinal connections. So there is a lateral vestibulospinal tract, which arises from our lateral vestibular nucleus, one division of this vestibular nuclear complex. And this projection is primarily an ipsilateral projection that runs down the spinal cord and terminates among the cell groups that are concerned with extensor tone, primarily in the lower extremities. So one example I've given you before would be standing up on a bus or train that is unexpectedly encountering bumps or jolts along the path. And so these are sensations that are being detected by the vestibular system, and in order to stay upright and not fall over as the floor is moving under your feet, there needs to be a moment-to-moment adjustment in posture, and that's what's mediated via this lateral vestibulospinal tract. Now there are other divisions of this vestibular nuclear complex that give rise to a medial vestibulospinal tract. And this projection is much more bilateral than our lateral vestibulospinal tract, and it's terminating among medial lower motor neuronal columns. And these columns are mainly found in the cervical region of the spinal cord. So one example of the operation of this medial vestibulospinal tract would be the reflexes that are elicited with a sudden forward rotation of the head. So what I'm thinking of is tripping and falling. So in order to brace ourselves for the impact with the ground, we want to get our face out of the way, so we dorsiflex our neck, and we often extend our arms to brace ourselves against the fall. So that's a reflex. So the forward acceleration of the head triggers this reflexive response that's mediated via the cervical levels of the spinal cord. That's our medial vestibulospinal pathway. Now, I want to make just a couple of points and then we'll be ready to move on. I don't want you to be confused about the nomenclature of these vestibulospinal pathways, especially the lateral vestibulospinal pathway. This pathway is somewhat lateral in the anterior and medial white matter of the spinal cord, but we still consider it part of our descending medial systems for upper motor neuronal control of posture and the more proximal muscles of the limbs. So consider together these vestibulospinal projections part of that medial descending system that adjusts posture and sets the gain of local segmental reflexes. One additional point I would make about these vestibulospinal connections is that they are operating on sensory feedback. So there is some kind of action that's being sensed, and then an adjustment is made subsequent to that action. So this is a feedback operation, adjusting posture in response to a sensory signal. Okay, let's move on and talk about the reticulospinal system. So the reticular formation is really a complicated network of structures that we find throughout the tegmentum of the brainstem. So indeed, the reticular formation is a complicated network of neurons that spans the core of the brainstem. One can even argue that it's continuous with the intermediate gray matter of the spinal cord inferiorly, and continuous with the lateral portions of the hypothalamus on the superior side of the brainstem. Well, within this network of cells, we now know that there are actually discrete circuits, and many of these circuits have specific functions with respect to visceral motor control and somatic motor control. There are elements of the reticular formation that do in fact project broadly and diffusely throughout the nervous system, and those are projections that have an important role in modulating brain function in various regions. Broadly speaking, we recognize the rostral part of the reticular formation coming from the mesencephalon and from the rostral part of the pons as having those kinds of projections that modulate activity in the forebrain. The more inferior part of the reticular formation in the caudal pons and in the medulla, that's where we tend to find these circuits that have a kind of premotor function. That is, they help to coordinate the output of lower motor neurons. Many of these lower motor neurons are concerned with visceral motor functions, including cardiac rhythms and breathing rhythms and perhaps even digestive rhythms. Other networks are concerned with somatic motor function, and here's where we imagine our paramedian pontine reticular formation coming in and helping to organize horizontal gaze movements. But there are other circuits within this reticular formation that are concerned with modulating the gain of segmental reflexes in the spinal cord, as well as making adjustments of posture. So to go back to the previous slide for a moment, I would highlight that there are indeed projections from this reticular formation down through the anterior medial white matter of the spinal cord, and then near their level of termination, they tend to bifurcate and supply bilaterally the medial columns of lower motor neurons that are found in the spinal cord. Now, one key way to differentiate the contributions of the reticulospinal connections from those of the vestibulospinal connections has to do with time. You'll recall that I made the point that the vestibulospinal projections are operating as a feedback circuit, taking a sensory signal, the movement of the head, and implementing a motor adjustment. So in this sense, the vestibulospinal system is operating based on information acquired in the past. The reticulospinal system is concerned primarily with making anticipatory adjustments of posture. That is, making adjustments of posture that anticipate the actions that are about to happen. So here's an example that helps me understand the differentiation of these two systems. Imagine a sprinter, and that sprinter is in the blocks awaiting the sound of the starter's pistol. So that sprinter has just heard the words ready, set, and now there's an anticipation. There is a time of preparation of the body, especially the lower body, for this explosive motor action of sprinting out of the starter's blocks and engaging in this pattern of locomotion that is essential for competing in this activity, the sprint. That moment of ready and set is where our reticulospinal system will be engaged in setting the tone of the segmental circuits so that an explosive motor action can be executed with maximum energy and performance and skill. So this reticulospinal connection is going to be especially active during this time of ready and set. It will be preparing the circuitry of lower motor neurons for this explosive action that's about to happen. Okay, now you're that sprinter, the gun's gone off, you've exploded out of the blocks, and now you're running down the lane in the course of this race. Imagine that you stumble. That stumble is not something that you planned, and it's not something that you necessarily anticipated. It just happened. Well, that stumble is going to involve some unexpected acceleration of your head. That will engage the vestibular system, and hopefully you'll be able to catch yourself and maybe break stride a little bit, but you'll make some adjustment, I trust, and continue on in the race. Well, that stumble and the adjustment that allowed you to continue in the race is a function of our vestibulospinal system. The vestibular system sensed the unexpected acceleration of the head, and an adjustment in posture and in the mechanics of locomotion were implemented via the vestibulospinal system. Well, I hope this image of starting and then running a race has been helpful and helps you to differentiate the contributions of the reticulospinal system from the vestibulospinal system. Well, if the reticulospinal system is going to serve to prepare you for action, to anticipate the activity that is being planned for, then it implies that it must know what that planned activity is all about. The implication anatomically is that there ought to be connections from our premotor cortex down to the reticular formation, and indeed there are. There are projections that emanate from our motor cortex that are informing these neurons in the reticular formation, probably bilaterally, about the activity that's about to be performed. And then the reticulospinal connections are those that actually make the appropriate adjustments of gain and muscle tone for the actions that are necessary. Now, there's one other structure that is often considered to be a collection of upper motor neurons in the brainstem that I want to mention. And it's found right here in the dorsal part of the midbrain. And what I'm attempting to identify for you here is the superior colliculus. Recall that the superior colliculus, it's one of the little hills that forms the tectum, or the roof of the midbrain, just above the cerebral aqueduct, which we see here. So there's the inferior colliculus, that's an auditory relay, and then the superior colliculus, which is the structure that I'd like to just mention very briefly here. So the superior colliculus is a motor structure that integrates sensory information from vision, from audition, from mechanosensation, and probably also from pain and temperature sensation. So these sensory signals are integrated in the networks of the superior colliculus, and a motor signal emanates out of the deeper layers of this structure. The superior colliculus is concerned with making reflexive adjustments of gaze and posture towards a sensory stimulus. So I already gave you the example of a bolt of lightning. Perhaps there could be an unexpected pinch of the skin, or maybe a sound that comes from some lateral position in our auditory environment that captures our attention. Either one of those three examples will often induce a reflexive shift of our gaze and our attention towards a particular stimulus. Well, how does the superior colliculus do this? Well, we've talked elsewhere about the role of the superior colliculus in coordinating saccadic eye movements through a portion of the reticular formation that coordinates movements in the horizontal plane or in the vertical plane. but there are also adjustments of the cervical spinal cord that are concerned with the turning of our head and the adjustments or the stabilization of our posture. Those adjustments that are mediated in the spinal cord are carried out by projections from the superior colliculus into the reticular formation, which then projects to the spinal cord. There may also be direct projections in the human nervous system from the superior colliculus to the lower motor circuits of the cervical cord themselves, but we know that at least there is a role for the reticular formation in mediating the signals that are coming out of the superior colliculus. So it's fair enough to include the superior colliculus in our conversation about upper motor neurons in the brainstem. Okay, we'll shift gears again and talk about the neural circuits for expressing emotional behavior.